running the Geoengineering Model Intercomparison Project, which I'm sure you'll talk about, GeoMIP for short. So Ben, welcome, and take it away.
All right, thanks. Sound good? I don't want to deafen anybody. Cool. So I'm going to talk about, I call it climate engineering, geoengineering, SRM. I kind of switch back and forth between them all. It seems like there's a new term every year, so I mean the same thing for all of them. And basically what I want to do is talk about what do we know and how do we know it. So I always like to start with the problem. This is a few years old where they did a bunch of Monte Carlo simulations using a simple model. What are our policies going to look like in terms of warming? So anything in red here is 2 degrees of warming and up, dangerous interference in the climate system. There's no policy, drill baby drill. We're already doing better than that. We actually have a climate policy, so that's good. Here's what we're doing now. Looks like about an 8% chance of staying below 2 degrees. If we keep doing what we're doing, more or less, so continued ambition, it goes up to around 9%. And then this one, Paris Agreement says that we should meet up regularly and continually pledge and try to do more. So starting to get into the 30s. So better, but I don't like those odds very much. Increased ambitions, if we do a lot more, that's starting to look more promising. So there's very little chance, according to these simulations, of going over 3. Not impossible, but it's looking okay. And then there's an illustrative 50% of staying below 1.5 degrees. So, not looking great. Why is 1.5 degrees important? Well, because a bunch of people said it was. Many people, including small island states, basically said if global warming goes over 1.5 degrees, they're going to be completely overwhelmed. This came out a couple years ago. There are new versions of it every so often. Basically, we're not going to stay below 1.5 degrees. And then this is a plot where they tried to look at when is it going to happen. And pretty much no matter what we do, we're going to pass 1.5 degrees sometime in the next decade. So, not looking great. And that's why I talk about geoengineering, because if we care about 1.5 degrees, we are doing this. That's a choice. We don't have to do that, but it's basically the only way to stay below 1.5 degrees at this point. So when I talk about uncertainty and confidence for what? What do we need to know by when to decide whether that's something we want to do? So there are lots of steps in the research process. So there's model-based research, which is primarily what I do. There's also field-based research, either observational or perturbational experiments. And then at some point, there's going to be this decision where if we say, yes, eventually we want to do geoengineering, if it still looks good, we're going to start switching things over into more operational stuff, like we do with weather. So forecasting, monitoring, things that we don't need yet. And so what do we need to know to make that decision is kind of where I'm coming from. So let's start with when, just to throw some numbers on this. Let's say we start deploying geoengineering in 2035. I have no idea whether this is going to happen. My ability to predict the future is basically non-existent, but it's a nice number to throw out there. If we work really, really hard, we can have a geoengineering airplane fleet in 5 years. That's probably a stretch, but I've seen people do amazing things. So that's by 2030, a commitment to deploy. That commitment likely needs to be based on negotiations, report, what do we know, what's the decision basis for that commitment. And those things take a while. And so we're talking about, a lot of the research for that report needs to be done by next year. I don't see that happening. But this is this is a really compressed timeline in terms of what we're working with. So you can move the horizon out as far as you want. We will obviously not know everything we need to know within the next year or even the next 50 years. That's not how decisions work anyway. But what we do need to figure out is what should we be working on first? What are the highest priority items? And this is going to be different for pick your favorite technology, pick your favorite scenario. I'm going to provide an illustration, mostly with stratospheric aerosols, but you know, all of this is a process. So this is something that I like to show. It's called a risk register. For those of you who've worked in industry, you've probably seen this quite a lot. For those of you in academia, this might be the first time you've seen it. It was the first time I'd seen it when Doug McMartin explained it to me. So basically on one axis we have the probability. Probability of something happening, probability of something going wrong. And then on the other axis we've got consequences. How important is that? So there's a high probability that when I walk out of this room I'm going to stub my toe on something because I'm a klutz. Not necessarily high consequence in terms of climate change, so we don't need to research that one. But if you do have items that are likely to occur or that we're likely wrong about, and they're really important, like if we get it wrong, that's really bad, that ends up in that red box at the top right there. That's a high priority research question. That's some stuff that we really should be working on. So next question is, how do we do that? So decisions are a continuous process. There's not just one magical risk register that we put together and then like that dictates how the field works. That's not what we're doing. But what we are doing is talking about how do we prioritize in the near term. So, you know, decisions are ongoing. What we learn will inform future decisions. How do we set up a framework to do this going forward? Which cans do we kick down the road? What do we not need to work on right now? I can't think of any research we're currently doing that we shouldn't be, so that's good. I'm not going to tell you what to do or not do. Keep doing what you're doing, that's great. But I do want to provide some more specifics. So I'm not going to talk about everything in this talk. There are some very important things that I won't cover. Governance. I'm a physical scientist, that's what I'm going to talk about mostly. Governance is really important. I like that in this field, natural scientists and governance experts talk to each other quite a lot. That needs to continue. There was a fairly recent National Academies report that talks about governance recommendations based on some of those interactions. We will probably need field experiments. Models can't tell us everything. And we want to make sure that the models aren't wrong in really important ways. And basically all I'm going to say is if you're going to go out and actually perturb the atmosphere, it should be worth it. So the risk of not doing it should be greater than the risk of doing it. You can decide what that means. There are lots of procedures for how to do that. One thing I will say is if deployment goes ahead, we're going to know a lot within the first year or even the first day of when we start deploying or when we even start building things. So what information do we need to know now versus what can we wait on and we'll learn it a lot better then? I don't have an answer to that question. I'm not going to talk about it, but it is important. We need observational field studies. Like that's, you know, going out into the world and observing the world. That works for climate change, it works for geoengineering, it works for a lot of things. We definitely need more impact studies, so things people really care about and are struggling with, like do I have enough food or water? Also very difficult, I'm not going to talk about those. So what I do want to talk about is how do we know what we know in geoengineering? So these are sort of the three pillars of science: theory, modeling, observations. Theory, we know. Like, we're pretty sure that geoengineering would work based on theory. It's thermodynamics, basically energy balance. I teach this stuff. Most people have learned this stuff. If you reflect sunlight, the planet will get cooler. We know that one. Models, we're really good at that one. There are lots of sources of uncertainty, but this is basically our primary tool. And it's not just any models, like these are well-validated climate models that have literally decades of getting the right answer for the right reasons. So we have confidence in that. Observations we struggle with. There are some analogs, so like volcanic eruptions for stratospheric aerosols. It's an okay analog, it's a pulse injection, the size distribution is different, there are all sorts of things that are just not applicable about it. Observations are really tricky, because thankfully nobody's gone out and done this. So we have to kind of fill in the gaps, and that's where I think a large source of uncertainty is in this field. So let's talk about uncertainty in more detail. There are lots of sort of flavors of uncertainty. There's this typical Hawkins and Sutton diagram where you can break uncertainty down into different processes on different time scales. So there's internal variability, like when is there an El Nino, how strong is it, that kind of thing. That's, you know, a source of uncertainty. There's model uncertainty. Our models are imperfect. They include or don't include certain processes. They do or don't match observations particularly well in some aspects. And then there's scenario uncertainty, which is basically predicting the future. What are our emissions right now? What are they going to be? How do you project that out to, in this case, the end of the century? So each of these different categories matters in different amounts on different timescales. Breaking scenario down a little bit more, you can actually start to pick at scenario versus strategy. So scenario is where you want to end up. So like, what's your temperature target for geoengineering? And then strategy is how do you want to get there? Do you want to do that with stratospheric aerosols and marine cloud brightening? If it's stratospheric aerosols, where do you want to put them? Do you want to put them in the tropics? Or do you want to cool the poles? Or do you want to do some combination of the two? There are lots of ways to get at a single temperature target. When do you want to start? What are the implications of a delayed start? Do you want to simulate interruptions or termination? All of these different things fall into different strategies. And then there's the technology itself. Is it stratospheric aerosols? Is it marine cloud brightening? Is it cirrus thinning? And so that's the one I'm going to talk about first. How confident are we in our knowledge of different geoengineering technologies? So, solar dimming. We are really, really confident in what solar dimming would probably do to the planet. So, this is a simulation done it was 25 years ago now, by Bala and Ken Caldera. And basically, their original simulation of geoengineering was to show that this is a crazy idea and it's not going to work. And it worked. So this world, you can see all these zeros here. This is high CO2. This is the effect of geoengineering as compared to the baseline. So pretty close. Geoengineering is not perfect. You know, you've still got these spots here, but it gets you pretty close. So that paper was published in 2000. Here's a paper where we looked at an average of 12 different models from the Geoengineering Model Intercomparison Project. We wanted to see, do all of the models show the same thing? And so you get a bunch of residuals, like you get this overcooling in the tropics and undercooling at the poles. All of this stippling is where the models don't agree on the sign of the response. The message that I'm getting here is the models all kind of show the same thing. You know, we kind of know this one. So this was in 2013, so we're using CMIP-5 models. Over here, we looked at what happens when you use CMIP-6 models, because GeoMIP has now been around for multiple iterations of CMIP. So up top is the results for CMIP-5, that's basically this one, but with different colors. Here's CMIP-6. Here's the difference between CMIP-5 and CMIP-6. Not that much. Yeah?
Sorry, just to clarify, the stippling is where they don't agree?
Where they don't agree on the
On the
sign?
And isn't most of the, at least tropical land surface, stippled?
Yes, but it's also mostly zero. So
But it's not compensating errors, that's not on this
it's not compensating errors. The models are all kind of doing the same thing, it's just they vary at precisely what latitude it shifts over from negative to positive.
And if we did the same for rain, would it look very different?
I can show you that, it's not that different. So the point being, we know this one. We're really confident in what solar dimming might do. Now, of course, it's possible that all of the models are wrong in the same direction, but this aligns pretty well with what we suspect it would do from thermodynamics, so we have some more confidence in this. So if solar dimming is relevant for stratospheric aerosols, which I think it is, we basically have to come to terms with the idea that from a physical science perspective, we're not going to see any showstoppers. We've had 25 years to come up with something, and we keep getting answers like this. I suppose it could show up, but it kind of seems unlikely. So, how relevant is this for stratospheric aerosols? And the answer is sort of. So, here is, so this is sulfur injection, this is solar dimming, and these are wind fields. So, they are different. Solar dimming is getting a very different answer than sulfate injection, except at the surface, oddly. So if you just look down at the surface, these look fairly similar. Not identical, but fairly similar. So this is where we could get into getting the right answer for the wrong reasons. And then we have to ask the question, do we care? So if you get the right answer for the wrong reasons, it is still the right answer. And so this gets into what's our goal? Do we want to understand the system, or do we just want to control the system? I'm not going to answer that question, but I think it should be raised. Now getting into solar dimming a little bit more, so we can look at Taylor diagrams. If you've never seen a Taylor diagram, basically this shaded area is good, everything not close to the shaded area is less good. So you can plot various things like surface temperature, maximum temperature, precipitation minus evaporation, so water availability, and you can do various sorts of strategies of solar dimming or stratospheric aerosols. There's one in there where we did solar dimming where we added stratospheric heating, because that is one of the main side effects of stratospheric aerosols, the stratospheric heating, which messes up the dynamics. So solar dimming is great for understanding some things, like climate system feedbacks. It's not so great for when you start caring about specific impacts. So utility is somewhat limited. So we're really confident in solar dimming, but how applicable is it is basically what I'm asking. So let's talk about stratospheric aerosols, because we can simulate those in models too. So these are also GeoMIP results. So here is what climate change is doing. Here is sulfate aerosols, and here is solar. So over here is the model mean, here is the model standard error. We are, I would say, pretty confident in the response to stratospheric sulfate aerosols. Not as confident as solar dimming, nor should we be, it's much simpler. But there are some things that all of the models are generally showing. And what I really want to point out is, if you look at the standard errors here for geoengineering, here's the standard error for climate change. It is lower for geoengineering than for climate change. And that's probably not because all the models are wrong in the same way. So what's going on here is you're keeping the model closer to its baseline. And when you do that, the feedbacks have less of a chance to operate. And feedbacks are where a lot of our uncertainty is. So in some sense, we know more about the response to geoengineering than we do about climate change. So that helps us with our confidence as well. That said, there are some issues in terms of model agreement, and models can disagree for a whole lot of reasons. So each of these is a different model. So we've got sulfur, solar, sulfur, solar. And they differ in stratospheric processes, circulation, feedbacks. Some of them have larger climate sensitivities than others. And so, yeah, they all generally look alike, but if you're talking about like, you know, is geoengineering going to alleviate side effects? I don't know if that's good enough. There are still some things that we really need to understand in here that the models are not telling us. To give you another example of this was a study where we did basically 4 different models, and we injected sulfate at 15 degrees south. And you can see where the different models put the aerosol and how much stays up there is really different. So the UK ESM, for example, 15 degrees south is the tropics. For CESM, 15 degrees south is really not. So this is the equator, this is 15 degrees south. So, you know, different models are really different. And we're going to have to reconcile that. So one of the ways we do that is validation. Are the models getting answers that are similar to what we know? So this is a validation of CESM against the eruption of Mount Pinatubo. And there are various ways to do that. And basically what you can see is that, so all of the colors are the model and the black are the observations essentially. This model does a shockingly good job of reproducing what happened after Pinatubo, with one really important exception. So Pinatubo injected 14 to 20 teragrams of sulfur dioxide into the stratosphere. We know that. There are tons of people who've studied that. In these simulations, it was 9.8. So that's what we had to do in that model to get it to match. That's not great, so clearly we're missing some really important processes here. And this is considered one of the best ones on the market. So, again, reasonably confident in many things, but there are still some major gaps in our understanding of stratospheric aerosols. So, I've been talking a lot about sulfate aerosols. Let's talk about other aerosols, because I know that's something a lot of people here are doing. I would say we are less confident, but still know quite a few things. And so there is a bunch of uncertainty in aerosol reaction rates, coating of solid aerosols by sulfates. I was really pleased to get a tour of all the fancy toys this morning. I mean, what you're doing can reduce some of these uncertainties in really important ways. One thing I will point out, one of the reasons I talk about sulfur more often than any other aerosol is because we've seen it. So large volcanic eruptions have put literal megatons of sulfur in the stratosphere, and we've been able to observe what happened. There's never been a large amount of any aerosol in the stratosphere except sulfate. And so that makes me a little nervous. You know, we want to bound those error bars. Actually, I was showing this slide to our advisory board. We're in a geology building, and they said, actually, the Alamo bolide a really long time ago put a bunch of calcite into the stratosphere because it hit a limestone bed, but I don't think we had satellites to observe that. So, you know, we need more work on this stuff. One of the things that really worries me, so there's this company called Stardust out there, some of you may have talked to them, and they have this sort of bespoke secret aerosol that they're designing, and they say, oh yeah, it's highly non-toxic, it's totally inert. If it's inert, will it bioaccumulate? They didn't have an answer to that question. But, you know, there is a lot of promise in these sort of alternate aerosols, solid aerosols, things like that. Careful research needs to be done. But we do know some things. We'll talk a little bit about marine cloud brightening. I would say I have a lot more confidence in stratospheric aerosols than I do marine cloud brightening, just because clouds are really hard. So there are some things we know. This is from a study of an Icelandic eruption, Holuran, that erupted for like 8 months. And so these are model simulations of what happened to clouds and liquid water path. Here are the observations. It's not bad. considering how difficult clouds are, it's the model's doing the right thing. And so we have reason to believe that our models are representing some really important things about aerosol cloud interactions. So that's good. And then there's this. So these are large eddy simulations where what they did is they had, so this is doubly periodic, so stuff wraps around. And they had, this is uniform seeding of salts into just the marine boundary layer where there are clouds. Here are 3 sprayers. You can kind of see them traveling this way, and then they wrap around and keep going. And this is just 1 sprayer. And so what you can see from this, so these are plots of albedo. It does brighten where the sprayer is, but then what happens is you get this dynamical circulation pattern on the sides where it actually starts to rain out the clouds. And at least for this one, when you calculate the albedo of the entire domain, it's darker on net. So it would be better if they'd never done anything. And that's something that the general circulation models can't do. These are processes happening on scales of tens of meters. So, I would argue if anyone wants anything to work on, please do large eddy simulations, because we really need to understand these fine scale processes. Are there things that we are missing just by looking at global scale models, and how important are they? I'd say this one's important. Cirrus thinning is still around. I would say we are not very confident in cirrus thinning. There are numerous issues with our ability to represent cirrus in models. So first, how do you represent cirrus seeding in the actual model? One of the ways we usually do it is by increasing the fall speed of the ice nuclei, or the ice crystals. That gives you the wrong size distribution, so that doesn't really radiatively represent what it should. There are also these simulations, and here's an example of overseeding, where if you get the wrong size nucleating particle or you add too much, you can actually, it switches between causing the cirrus to fall out versus actually building more cirrus. And so you can get the opposite sign of what you want if you're not careful about it. And then models are really not great at upper tropospheric ice water path. Very few of them match the observations, and so this presents some difficulty. And also there's lots of intermodel uncertainty. The models are doing very different things for very different reasons. So ultimately I think if we're going to continue with this one, which is a pretty big debate, there's a lot more work that we need to do, which would benefit our understanding of cirrus in general. So, overall, some confidence in some technologies, some that we're working on, some maybe not so much. And now I want to talk about that diagram, so process and time scale. I will start with internal variability. So there are ways that we can study internal variability and how geoengineering might affect internal variability. So this is a simulation, it's called ARISE SAI. It's a 10 ensemble member simulation. So 10 simulations, slightly different initial conditions, so they have different weather but the same climate. And the neat thing about ensembles, and especially larger ensembles, is you can start looking at extreme events. Extreme events are by definition rare, and so you need a lot more data to be able to look at them. But you can look at things like, well, those are consecutive dry days and consecutive wet days. These are part of the standard extreme indices patterns that we can use to look at how will geoengineering affect extreme events. You can't just push this to its limit, because if you double the number of ensemble members, you increase the signal to noise ratio by square root of 2. So 100 ensemble members get you an increase by a factor of 10. And 100 ensemble members is a lot of computation. So, use this judiciously. But there are ways to get at extreme events or other rare events where you really need to understand what's going on with variability. Model uncertainty. So I showed this one. There is model uncertainty, of course. How important is that? Like, how much do we care whether our models are wrong? And so I want to show you just a quick slide where we introduced feedback into a climate model. So basically what we said is, here's RCP 4.5. This was 10 years ago, so that was the scenario we used. We ran this model a whole lot, so we really understood its sensitivity. The blue line, what we said is, okay, let's pre-program how much we need to turn down the sun or inject into the stratosphere to reach that dashed black line. The red line is where we said, we're not going to pre-program anything, we're just going to say, all right, in 1 year, let's see how far off we were from that black line. If it's too hot, do a little more geoengineering. If it's too cold, do a little less. Feedback works. You do this all the time. I did this when I checked into my hotel and I went to take a shower. Like, I don't know where to set the knob. You have to fiddle with it a little bit to figure out where to do that. That's feedback. If you drove to work, that's feedback. You didn't memorize every single road and every single turn. You know, if you want to go left, you turn left. It's a heuristic. These down here, we deliberately threw off the model sensitivity because we wanted to see how much uncertainty can feedback handle. So we threw it off by 50% in either direction. Feedback works really well. The predictive one does not. Like, you know, this is 50% of what it needs to be. This is 50% too much, as you might expect. But the feedback is pretty robust. And so, why am I saying this? Because this allows you to compensate for some amount of uncertainty. So this is a RISE SAI, but in two different models. This is the UK model, this is CESM. These are very different models. If you look at sort of the model genealogy, these are more or less independent. Very different injection rates. So if you look at the injection of different locations down here in the total, really different between the two models. But if you look at the lines up there, they both pretty well match the dashed black lines. So feedback works. And so I think it's worthwhile asking the question, okay, we don't know everything about the models. Is that good enough? Like, do we know enough to meet our objectives? Or if you look at these and you say, you know, there's some features there that make me really worried, we may want to pay more attention to that. I don't have a good answer for you, but at some point, you know, since we're not going to know everything before we make a decision, we as a society are going to have to come up with what's good enough. Scenario uncertainty. So, you know, feedback's really neat. It works. And geoengineering is, like, you can just kind of inject a whole bunch before it starts to get too weird. These simulations over here, we're offsetting 5 degrees Celsius of warming, which is ridiculous. I wouldn't want to do that in the real world, but you know, you could. So you can kind of get any answer you want in terms of scenarios. And there's no end to the number of scenarios out there. Like you could say, you know what, 1.5 degrees is too ambitious. I want to do 1.6 or 1.7. And you don't want to have to run a climate model simulation every single time you do that because each one of those takes a month. So this is where emulators could be really useful. Doug McMartin's group, one of his PhD students, has actually built one. There are a bunch of other people around who have built them. You can explore a bunch of different scenarios in these. And so what will happen in the future and how much does it matter, that's starting to become a tractable problem because you can explore a bunch of different scenarios. Emulators can get very complicated because to some degree climate engineering can be designed. Like you can get different answers depending on the latitude where you inject or the season where you inject. You don't have to memorize all of these, just note that each panel is a little bit different. Some of them are a lot different. So if you want to cool the northern hemisphere more, inject more in the northern hemisphere. So a lot of room to explore different consequences and different side effects. Okay, so I basically talked about many, many different forms of uncertainty and a whole bunch of stuff that we don't know. What do we know out of all of this? You know, I've been working on this since 2007, and I don't want to leave you with the idea that we don't know anything. So we do know a lot of things. So let's start with, what do the models say about temperature, specifically temperature change? If you increase CO2 and you turn down the sun, I've shown you this already. This is an average of 12 models. Climate engineering is imperfect. You get an overcooling of the tropics and an undercooling of the poles. Okay, so, but that's a high CO2 world. I didn't even plot the color bar because it's just off to the right. So the geoengineering one looks a lot better than a high carbon world. And we kind of get the same answer when we talk about precipitation as well. So you've probably heard the trope, geoengineering would reduce the monsoons. Well, yeah, it might, depending on how much you do. But also, look what's happening under a high CO2 world. You get this massive acceleration of the hydrologic cycle. And it's not a simple case of more rain is good, because how does that rain fall? If it all falls in very extreme events, we call that flooding. That's not great. So you can actually get a situation here where areas are receiving more droughts and more floods, even though the average rain might look good. So precipitation goes down, but it would have gone up under global warming. We kind of get the same story for sea ice, heat waves, floods, droughts, ocean heat transport. Basically, most of the things that I have looked at from climate models, global scale climate engineering is not perfect by any means, but is better on average than doing nothing. Or, well, continuing to emit. So this is a paper that I think Pete was here when he worked on this. So who is it better for? And so each of these dots is a grid box from a climate model over land, so where people might live. If one of those dots falls within a blue area, that means climate change does something to that area and geoengineering brings it back. It makes it better. If it falls within red, climate change does something to that grid box and geoengineering makes it worse. So you can look at anything you want from these. Moisture availability over here, flooding events over here. You kind of get the same picture. So for, I think it's like 99.5% of grid boxes fall within the blue areas. So climate engineering is, under these metrics, better for most people. Now, if you live here, you might have some things to say about that. And different models have different ideas as to where that dot is. So this is just sort of an aggregate picture. Termination shock. He actually got that title from our community. I forget who exactly he talked to. But this is the termination shock. So business as usual. If geoengineering is the only thing we do, we better not stop. Because if you stop, well, you still got greenhouse gases in the atmosphere. The climate's going to rebound in about 10 years. So, you know, if you believe that adaptation is a function of how long you have to adapt, or adaptation difficulty, then in that sort of situation, it'd be better if we'd never done geoengineering at all. Now, this does suggest a few things, namely, don't do that. So it suggests things about how robust do systems need to be so that this isn't a risk. Or maybe, so if you look at this, it's a rebound of 4 degrees Celsius. Maybe there's a cap on how much geoengineering we would want to do. You don't want 4 degrees Celsius, maybe 1 is the maximum amount of geoengineering you'd want to do. So this has some important implications. Some general things that we know from all these. Climate engineering is imperfect, but it's a lot better for most than climate change. I've got an asterisk on there, I'll come back to that. To some degree, you can design it to reduce side effects. The map I showed you of the aerosols in different places, depending on where and when you inject, it's a little bit tailorable. You can't get rid of all side effects. There will be trade-offs from this. In some sense, this is a good thing because it's, you can't say, hey, I want to target Romania for geoengineering. It doesn't work like that. So it's not weaponizable in that sense, but that also means there are going to be side effects. There are going to be winners and losers. That's just, we'll have to deal with that. Termination risk depends on how much we do. And so, what does better mean, and for whom? That's really important. And to some degree, this is a function of how we measure it. So, all of these are basically showing the same thing. So here is climate change, so no geoengineering, going all the way down to a lot of geoengineering, so more cooling. And then the other direction is just how you're measuring it, what's your baseline. So you can get very different answers depending on when do you want to go back? Do you want to restore to the 80s, or do you want to keep things at present day, or are you okay with a little more warming? All of this really matters. It's made our communication in this field really complicated because if you want to present a complete picture, you kind of have to show a lot of panels and say, which one do you like best? But it's really important to do that because what geoengineering does is it sort of breaks that relationship between global temperature and regional effects. Under climate change, everything kind of scales with global temperature. Geoengineering, it doesn't. It starts to introduce choices. And so we have to present those choices. So how should this be used? This is what I often refer to. I know it's been criticized, that's totally fine. There are things we can do. So here's business as usual. We have to cut greenhouse gas emissions. That is the only permanent solution to climate change. That will not make things better. It will just keep them from getting worse. Greenhouse gases stay in the atmosphere a really long time. If we want to make things better, we have to actually pull carbon dioxide out of the atmosphere. This sort of time scale here, it's probably 150 years, something like that. So what do we do in the meantime? Do we just kind of live with the consequences and whatever this overshoot is, we're just okay with it? Or would we use climate engineering to buy us some time while we ramp up those negative emissions? I don't have an answer for you, but I think it's important that we think about it. Note that this is not saying that any of these are substitutes for each other. We cannot just do climate engineering. So let me tell you a couple of things that we're doing at IU, and then I'll wrap up. It's my talk, I get to advertise my work. I don't have any results for this yet, but this is something we're working on. A lot of people want local information. And so the question is, how do you get local information? Dynamical downscaling is a great way to do that. So you take the output from the global model and you use it as boundary conditions for the regional model. And so we've done some of this for climate change over Indiana. Everybody seems to ignore the Midwest. I live there, I'd rather they didn't. And you can see it is better. So here's the global scale model. Here's the regional model. You can see there's a cold front right there. Lakes are actually colder as they should be. You can see cities, you can see mountains. There is added value to this sort of thing. And so the question is, what's the right way to do this? Because we want to make sure that what we're doing actually does add value and is not just a way to get wrong answers more precisely. So no results yet, but these are some fun things that my student did, like turn down the sun over Bloomington by 20% just to see if he could do it in the model. The simulations that are more realistic are running right now. So that's one thing we're working on. Another thing we're working on, who's going to be making those decisions? So And I think the people who are in classrooms right now are going to have a say about this in a very short time. Climate engineering is in the next generation science standards. It is required that students learn about this in high school. Right here, this standard, large-scale geoengineering. How many high school teachers do you know who are teaching this? So we are. We run workshops with high school teachers where we've introduced them to this topic and we teach them how to teach it. And then there's an activity where we actually went into a high school and they showed us what they were designing, their actual engineering designs. It's a great way to bring engineering into a classroom. Like, high school chemistry is not a good way to bring engineering in, it's unsafe. But, engineering design, we can do that. So what was really cool is all of these students, they presented ideas that they had come up with, and I was able to say, let me tell you why that's cool, or let me tell you who else is working on that. And some of these students, like, this can be at any level. This particular class, I guess it's technically a remedial class. It's students who are not ready for AP Bio. These are students who have basically heard no their entire lives. No, you're not good enough. No, this isn't good. No, you're not ready. So, like, they got to hear an actual scientist telling them, here's why this is cool, or this will work, and this guy is researching it. So we actually have a teaching module up there if you want to go check it out, or email me and I can send it to you. So what should we be working on? Because I've presented basically just a ton of stuff. Really depends on the mission. What do you think the decision is going to be about? So in this idea of the risk register, we came up with some things. Just as a list that Doug and I came up with, things that we thought were important. Aerosol microphysics is up toward the top. But, this is our list. It's based on what we thought about. Everyone else would come up with a different list, and that's great. We as a community need to have that conversation. And that's not to dictate who is working on what. Divide and conquer works best. But, maybe if we're all talking about it and coordinating it, we can kind of use the benefits of having a community. It's also worth keeping in mind that this is not just about science. So these are results from GeoMIP. GeoMIP has become kind of an entry point for different people who want to get involved in this field. It's sort of like, hey, I can run a model. What simulation should I do? And the first thing I told them is, can you do a solar dimming simulation? Because everybody can do that one. So then they immediately become part of a community and a contributor. That entry point is really important. Large ensembles. So this is a study done by a team out of South Africa, looking at just a free data set that we provided for them. There are lots of developing country teams out there right now who want to learn about this topic and want to get involved, and they need a way to get in. If you can't run your own model, can you work with data? We have it. We can get it to you. We've literally handed people hard drives at meetings to get them data. So, this sort of topic and what we're providing can help people as an entryway into climate science or into learning more about how this topic might affect their country in the coming years. So, we're generally doing a decent job. There's always more to do than there are people. I would say that. Let's keep the mission in mind. When we start to do a new study, let's ask why. Why are we doing this? What do we hope to learn? I'll say this anyway. We're going to pass 1.5 degrees. If we are serious about this topic, we're doing geoengineering. And so let's not screw it up. That's all I've got. Thank you.
Thanks very much, Ben. I'm sure there are questions, comments, et cetera. You covered a lot of ground. It's great. So if you have a question, comments, raise your hand and you come around. Holly, nice to see you, by the way.
Thanks so much for that talk. I was thinking about the question of how we measure progress in reducing uncertainty. I was doing an event last week with a scientist who said that he was really confident that he knew what would happen if we did sulfate aerosols. That was a different message than 5 or 10 years ago. And as a person who's listening, I don't know if that's because the science has advanced that much, or his personal opinion has shifted, or if he just felt more comfortable in the current climate saying that and didn't have to calibrate the messaging. But like, is there a framework that you all are working on where there's maybe some interface or system where you've listed, like, here are the 50 things we need to do, and you can just check them off and the public can see, like, kind of pre-registering a whole research program or something like that?
So, gosh, where to start with that question? So I have a feeling that the reason that person was saying that is probably all of the above. There's a lot happening all at once, and it's, it's hard to keep up. As you know, because you and I have talked about this, I would love it if people would pre-register what they're doing and what's going on and what they want to work on. I think transparency is really important in this field. And, also practically, like, I have nothing on that. I would love it if more people paid attention to this stuff. That would be great. In terms of the actual root of your question, I don't know. I'm not sure the best way to go about that sort of thing, but I think it's important.
I am from biology side. Very interesting talk. You mentioned the removal of carbon not necessarily will decrease the temperature increase. It takes a few hundred years to have any effect. Just about 10 days ago or so, there was a paper from Australia, a group of people mentioning more or less a similar point, that regardless what we do, the temperature will keep increasing for another 200, 300 years. I don't know whether you have read that paper.
I've not.
It just came about less than 2 weeks ago. It was a theoretical model. So now, spreading this knowledge to the community, you are doing an excellent job. My concern is, unless the policy makers implement such ideas, such philosophies, so now in spite of spreading the knowledge has less effect. That's one thing. And as a biologist, I feel more about the biological diversity.
Mm-hmm.
Whereas the geoengineering people, they are, in my feeling, they are more concerned about human comfort. So now, I don't know how much they are worried about biological diversity.
So I would say that this community is very worried about biological diversity. One of the seminar speakers that we invited out just a few months ago is an ecologist, and she talked about geoengineering. And you don't have to care about biodiversity or ecology. You can care about the food chain and how we eat. Like that's what biodiversity is. And so I think we are very concerned about it. It's just it's a challenge. So the first GeoMet meeting that we had was in 2011, and it was basically a bunch of volcano nerds talking about recent eruptions. And that was a lot of fun, but that's not the whole world. The first time I ever heard anyone mention the carbon cycle in this field was 10 years ago. We've got a long road to go and we need some help. So I would love to see more biological and ecological work in this field, but we need the people, we need the experts. In terms of your other question, I do want to be careful with that because more knowledge isn't always the answer. People absorb or do not absorb knowledge based on their values. And so I would start there. What do people care about? And how can you get this in front of them in a way that they would care about it and can make informed decisions.
I'm Skyot and I'm a health policy researcher. I'm curious if you're aware of any models that have framed geoengineering as a health intervention or looked at the human health risks, and what the state of research is on that front.
Very few. So there are a couple of studies looking at the effects on air quality, fairly minimal in my estimation. Beyond that, so I would argue that the intersection of climate science and health is fairly new. I'm involved with the American Geophysical Union. I'm on the program committee for their big meeting. GeoHealth, I think, is a section that's like 5 years old or something like that. And there's so many aspects of health: heat waves, water availability, water quality. Like, you can't drink water with parasites in it. Vector-borne diseases, mental health. It's a really important area that needs a lot more attention. Yeah.
Thanks so much for the talk. I'm a geographer, so apologies if these are a bit basic for most people in the room. But I was wondering, early on you said that we'd need to do field experiments, and I was wondering if you could talk a bit about the kind of barriers for conducting field experiments.
I would probably defer to some other people in this room. I am not an experimental person. I work with computers for a living. What I will say is that there's no way that models will give us all of the answers that we need. And so it's really important to figure out where those gaps are, and are there real world experiments that could be done that could fill those gaps? Or are some of those gaps irreducible and there's just no experiment? I think we need to work on that. And then if we know what the gaps are, there are very smart people who can design field experiments. But that's about as far as I can talk about that. Yeah, please.
Have you modeled the effect of solar dimming on agricultural production?
Yeah, indirectly. So solar dimming itself, just turning down the sun, I would say the results are mixed because plants really like photosynthesis. We're talking like a 1% or 2% decrease. But plants also hate heat, or at least some of them do. And so it depends on how you look at it, and different answers can get you different things. When you start adding sulfate aerosols into the mix, you get a lot of forward scattering, so more diffuse light, and that can penetrate canopies, and so some plants really like that, some plants probably don't care. It's complicated, I'll put it that way. Yeah. Yes.
Thanks for the talk. I'm wondering about two sort of different conceptions about the timeline of deployment that I saw come through in the talk, and how going one way or the other might bear on your research agenda. So one is the thought that's on the slide here, which is like, we're going to pass 1.5, say, in 6 years. And so we'll need to deploy, if we care about that target, then or relatively soon after that. And so we should sort of be focusing on these like high value, like let's just rule out the worst case scenario type research.
Mm-hmm.
And then the other framing, I think, kind of came up earlier in the talk, which is like, we're not going to know all that we need to know in the next year or the next 50 years, you said. And that view kind of pushes me in the direction of like, we should wait to deploy, if we deploy, until we know enough, regardless of what level the temperatures are at that point. And that might kind of guide your research agenda in a different, maybe slower direction. And so I'm curious where you fall on that divide, if anywhere.
Yeah, so I think I didn't communicate that terribly well because I don't see it as a divide. I think that there's an aspect of both. So what we need to do is look at what do we need to know and by when. So if there's going to be a decision in, I don't know, 2035, something like that, what do we need to know by then as sort of a de minimis set to be able to understand, yes, we should, or no, we shouldn't. And that will not be everything, but it will be some things. And also, if there are some things that we won't know, can we set up frameworks for how we will learn those things in the future? So basically what I'm kind of saying is we need to organize the research. University research is basically PI driven, so I work on what I'm interested in. And so the title of the paper that's associated with this figure is called mission driven research, where, and there are federal agencies that do that, like NOAA, for example, or the National Weather Service. Their mission is to protect life and property. And everything they do goes to that mission. And if you are interested in a topic that's not related to that mission, well, you can probably work on it, but you're not going to get funded for it. And so that's kind of what I'm arguing. Let's organize, let's figure it out systematically, and beyond that, we'll just have to do the best we can.
Yeah. So, great talk, thank you. You kept saying you think the GCMs we're pretty confident about GCM results at this point. But two things. One, you said that we haven't done a field experiment of actual deployment of any scale, so we don't actually know like how the microphysics will act, how, if the sulfate aerosols actually coagulate and fall out very quickly, then it's not going to work. And then the other thing is that GCMs don't necessarily do a great job with stratospheric transport. You had a lot of the different zonal mean distributions, and some of them were kind of like, showed the aerosols going to the poles pretty quickly. Other ones had it more confined. And then on top of that, there's a lot of research right now into the role of the stratosphere in surface climate kind of broadly. There are open questions there. So kind of what do you say to someone who thinks that kind of the state of GCM research isn't really sufficient?
Before I answer that, are you Mariana's student by any chance? Or?
Former student.
Okay. That makes a lot of sense.
I had to represent.
Yeah. Yeah, I don't want to overstate our confidence. I'll put it that way. There are plenty of really important gaps. For example, in stratospheric transport, that is an important one. And I think the question we need to be asking is how much do those matter? So, for example, this slide right here. I guarantee you both of these models are doing stratospheric transport very differently. UKESM, like the tropical pipe, is really robust, whereas CESM it's not. But those uncertainties are ones that we can manage, because in both models we're able to meet the goals we set out. Now, that's true for this set of goals. Maybe there's another set of goals where that wouldn't work, and that represents an uncertainty that's not tolerable. But I think your question is really important and also situation dependent. Which uncertainties matter for what? And that's something we need to figure out. Yeah.
Thanks for the talk. I know you said that you weren't going to talk about some of the governance issues. I'm over the law school, so I'm interested in governance issues. And I'm kind of curious as to the extent to which your scientific research and scientists are collaborating with either government institutions or legal scholars in terms of trying to devise a framework for actually implementing this stuff.
I mean, the person who invited me here sitting right in front of you knows a hell of a lot more about governance than I do. So, no, we do talk quite a bit about that. That's one of the fun things about this field. Like, I go to a conference and I have friends from any discipline you can think of, and we work together and we really care about these sorts of problems. So I'm not a governance expert, but I know who they are. Or at least some of them. And so that doesn't really answer your question, but it helps me sleep better at night knowing that there are smart people who care about this. Yeah.
I'm Greg Byer. I work in sustainable finance. You've mentioned transparency a bunch, and that's our big thing. What what formal efforts are underway, if any, to generate a lot of real-time transparency in the work in the space between people, groups, data, funding, the whole thing?
Yeah.
Particularly to keep an open ontology so nothing gets bleached out
Yeah.
by biases.
Holly and I have, with Shuchi Chalati, have an opinion piece that's submitted right now where it's basically sort of a screed as to how easily people can hide money and they shouldn't. Should this work be funded by fossil fuel companies, for example? I think that's an important question. It becomes an even more important question when you start to realize that fossil fuel companies can funnel their money through someone else and it doesn't look like it's a fossil fuel company. That just kind of squicks me out. And so I'd like to see a lot more effort toward transparency than there currently is. If you ask any researcher who's funding them, they'll tell you. We don't really have anything to hide. We put it in our papers, et cetera. But that's very different from a sort of centralized effort aimed at transparent communication. And I haven't done that just because I'm busy. But I think it is really important and long overdue. Yeah.
Hi, I'm an undergraduate here, writing a senior thesis on the geopolitics of solar geoengineering. And so I'm interested in kind of the diverging preferences of various interest groups and nations in relation to SAI, and particularly in how these models might be able to represent those diverging interests. I noticed the kind of two-axis diagonal graph that you had, where one was the kind of whether the effects of climate change will be reversed or exacerbated.
Yeah.
That there's kind of this notion of reversal being good and exacerbation being bad. And so I'm curious whether how sort of the diverging interests may be incorporated into this kind of.
Yeah, and you rightly pointed out simplification, that going back to where we were is better. That may not be true. It also depends on when, going back to a month ago might be okay, going back 50 years might not be because we're already used to what we have now. There are lots of diverging opinions, I'll put it that way. And I think, at least from my own experience, a lot of them deal with any kind of reason you can think of. So I talk with a lot of people from developing countries who are a lot more open about this topic than some others, because they're sort of like, if this could help, we're suffering, let's look into it. And it's not necessarily that they're pro or against, they just want to be able to form their own opinions without, the past colonial or imperial interference. And so there's the degrees program out there is aimed to do that. It's sort of democratizing climate science. I talk about this topic with my students. So I teach a climate change class. And I'm in southern Indiana. That's Trump country. So I never really know who I'm going to get in my class. And so I start out the class with a pre-test. If you are concerned about climate change, why? If you're not concerned about climate change, why not? Or if you don't know anything, what do you hope to learn in this class? And I kept thinking, I'll get this mix and that'll be my class. Out of 25 students, 23 of them were along the lines of, I don't know why I'm here getting this degree, we're all going to be dead in 20 years, why bother? And so, the first time I saw that, I basically redesigned my entire class, and like a third of it is now on hope and solutions. And I do a day on geoengineering in there. And then I ask them, what do you think about this? And the answer that I get is, it's not a great option, but thank God we have something. So there may be a generational aspect to that as well. I'm not sure if I could really give you the full landscape. That's just what I've seen.
Time for maybe one more question. and I have one if nobody else does, but I don't want to be the one to ask it. My question is more of a follow-up. You had the slide with the red questions or issues that for you and Doug at least are the most in need of future research. And I'm wondering if you could just sort of walk through a few of those. Yeah,
This one?
Yeah, exactly. The top 2 or 3. Just I'm curious.
Yeah. So I mean, this is heavily based on just what we've observed and what we're interested in. So which ones do we think are in red? So we put aerosol microphysics up here because that really matters for stratospheric transport, stratospheric heating, a lot of side effects. That's one that we really don't want to get wrong. Subgrid scale mixing. So there was the question over here where when you spew sulfur dioxide out the back of a plane at that temperature and pressure, will it just coagulate and sink like a stone, or will it actually disperse the way we model it to? I looked into this a little bit more. It's actually not obvious, so and that's really important. So we put that one in red. Ecosystem response we put in red because we basically don't know a whole lot. So that's a few examples.
Excellent. All right, one last round of applause for Ben. Fantastic. Thank you so much for coming, Ben.